It's late morning, July 6, 2017. I'd like to present my interpretation for the Pith Ball type experiments I've been working with here recently in the past several days. I may get to that in this to some extent. What that's going to end up presenting is a different concept of covalence. Right now, there are so few electrons assigned by the standard model of the atom that the concept for covalence would be, it would be similar to what I'm going to present, but when you have so few electrons or orbiting hovering type particles, it really gets to be very exclusive or narrow in its application. What I'm going to suggest is, we'll see this atom model that I'm presenting, in which everything has to have mass, and it also has to make sense with regard to the size of atoms and then density. You can't have all of the mass in the nucleus like the standard model tells us to set that up. It doesn't work when you check it with density. If you assign the size of atoms, it doesn't matter how, it matters as far as reality is concerned, how large you make your atoms in your model, but everything has to be proportional. So the density problem collapses it no matter what. But anyway, in this model, since everything has mass and all radiation has to have mass, you know why this has never been explored, I think, has been because of religion. Having things that don't have mass going around doing things. That's just like, our calendar is set up from when Jesus was born, okay? That should tell you something about our culture. This is 2017, roughly 2017 years since approximately when Jesus was born. Okay, so as far as Jesus being said to have walked through walls after he allegedly rose from the dead, all those kind of things, it just really suits the way the culture has been with this religion forced upon it by the Roman Empire for centuries. That you have the first atom model that's created, and particle system. You have things without mass. Of course, that's in the future. That's probably going to be viewed as crazy, but right now, people think that's possible. I don't think that's possible. I think it can all be explained. It's a little bit more difficult because you have to nail these explanations perfectly. But I think it can all be explained with a system where everything has mass. But anyway, with that kind of a system, these shells would have lots of mass in them that are out from nuclei, and there would be several layers of them. And then those atoms that are large enough to have like beta electrons, or maybe even some positrons orbiting, those would be much farther out. And most of the smaller atoms, up to the middle-sized atoms, wouldn't even have those. I don't know where the breakoff is. I thought it was going to be iron. It's probably larger than iron. But, what we have right now, we have something that is a substitute for reality. It's something we use. We say, well, it's a way for us to pretend that we understand it all. That's what it is. It's something somebody came up. It's a system where you have these paired electrons doing this and this, in this shell, this and that. But that's all artificial. It doesn't even stand up to a density test, okay? Those shells are these radio particles that we interact with every day. They all have mass. And you know, they would, you send those out by electric current, uh, electric current oscillations by hertz. By reversing the current quickly, you can get, in different materials, you can get different kinds to go out in the way that you want them to do. All you have to do is adjust uh, these levels of the current and the hertz and all the reversals of direction and all that kind of stuff. And you can try it until you get the results you want. And so, but these are radio particles that have mass. Anyway, I'm going to present a new idea on covalence. You would call it covalence because it's conceptually similar to what's considered right now. It's where two atoms would share electrons, let's say. Well, and when you look at water, several water molecules combined, making a sphere or a rounded shape, say, droplet in atoms that are next to atoms that are lensing in cotton fabric. When you wet the cotton, you can see covalence. You see the water molecule, or there's several of them together, and you can't see that they're individuals. That would be covalence. And when they start to separate, and then they're smaller, and they're moving a little bit back and forth, unlike all of the atoms that are attached to the cotton fibers that are standing still. They're not vibrating. They evaporate. They disappear one by one. So, you know, that's what confirms that that I was actually viewing atoms in cotton fabric, and that's what this is based on. You take what a person can see there, what I've seen there several times, and you say, okay, well, if these are atoms I'm looking at, okay, well, then how would that be arranged and what's going on? Okay, so this idea of covalence is going to be like that group of water molecules with the outer radial shell apparently covering all of them, so that they're not individualized. And this probably goes on in some solids, or a lot of solids. There's probably a reason why some materials have atoms. Let's say a solid like zinc or cobalt or tin, whatever. Let's say phosphorus. Let's say potassium. Let's say cesium. Some of those are going to have individualized atoms, and they're allotropes, the structure, that is. And the reason they would have, I think why they would have individualized atoms, not just covalence, and they would be basically come up against one another and then make a structure, whether it's amorphous, has no structure, they're just piled on one another, or they actually form a structure, which would be an allotrope. But anyway, regardless of which one of those they make in their solid, or this could be a liquid or solid. Of course, not a gas. Gases, they're not attached. Only maybe pairs are attached, or triplets sometimes. But anyway, their outer radial shell is filled, and so it's standing still. They can vibrate. There's your vibration. They can vibrate. You wouldn't see it if you're looking at atoms lensing in cotton fabric, but they vibrate. They have to. They're being pelted by radiation particles, and so these would come up next to one another, and whether they make a structure, some sort of a distinct structure or not, and they would be repelled surface to surface. Those outermost radio shells that are filled, and they would all be the same, roughly, and then they would stick, and they attract, they attach, they stick, and then they make a solid. And so that's what I'm going to say is when you have those shells are filled, you're going to have that kind of structure. You're not going to have any, there's no reason to have any of this covalence. I think in good conductors, this covalence is going to be where you have from 10% to 50%. If it's less than 10%, it's so scant that you'd have a little orbiting shell there, like an electron shell, but it's not going to be that significant for transferring electric current across through the material. I think it's going to be from 10%, and it gets pretty poor at 50%. I think in the 10 to 20% range, that the shells, the outermost shells are filled. Then there's instead of having a line that orbits, you get more of the effect that you see with what I saw with the water molecules in the cotton fabric. That there's going to be some sort of transmission of those particles flowing over the material, all over, maybe through it and over it, but there's going to be some kind of covalence, and that's probably the leading cause in why electric current is passed from one side of, say, a copper wire, one end of a copper wire, to the other end so quickly. Is probably that covalence. Now this covalence that I'm going to suggest and explain, it's going to need to transfer particles at near the speed of light. Is it moving at near the speed of light? No, it is not. That's one of the problems of this. Okay, how can it transfer these? What I'm going to say is that the electric photons can, I'm going to explain why they can fairly easily supplant a lot of those radio particles in that covalent shell that's circulating in and through and around many solids that don't have filled outer radio shells, which makes them good conductors. Okay, the reason they can be transferred at or near light speed is because of attraction. The attraction to those is such that it speeds up the transmission, the flow. It speeds up the flow. There's going to be added repel because of these electric photons. I'm going to explain how they can supplant. When there's a plethora of those presented as part of the environment next to, a group of these atoms that have this covalence already going on with radio shell particles. Okay, and what it is the electric photons, by being singles. Now they are the same photons as are in many of those radio particles, but they're individuals, and they're not needing to neutralize a center uncharged or more likely low charged photon. See, that takes away some of the repel of the radio particle. Now these radio particles are caroming. They're not held basically in static positions, though they vibrate in a filled shell. They are held to orbit and circulate, but they're not held in positions. That means they can carom when they're struck. When they carom, some of them get out of line enough, instead of maintaining the right distance from the nucleus, that gives the opportunity to electric photons to supplant one or two or several of those. And so then this is what happens in static electricity. Is when you stir those up by rubbing the PVC wand, let's say, then you're causing by that friction, you're causing a lot of those shells, and they wouldn't necessarily need to be a good conductor. That isn't a good conductor. You're causing a lot of those to be lost, and the electric photons are standing by when they lose their position. Now they're preferred in the long run, but when they lose their position by this rubbing, by this disturbance, and you have the same thing in a rotor that turns in an electric power plant, when you have this disturbance that's going to create static electricity, these electric photons are standing by and they come in and fill those shells. They take the places of, depends on how much disturbance you create, they take more places. This is why you have repel. When you observe in the video I did of where it showed, let's say, the conductor, the little bead conductor with the aluminum foil on the surface of covering over a styrofoam bead. This is why, the reason the attraction happens. Okay, there might be a hole as well. I'll talk about that later. But it's actually transferring electric photons over into the conductor. The conductor has these unfilled radio shells on the exterior circulating in and around and through the material, the aluminum. And so when you put it the one next to it, now you've loaded it up with those, and they're more fleet, see? The reason they can supplant is when radio particles are lost, these are going to beat those back to occupying those spots over a nucleus. So, and it lasts. We saw on last Saturday, I didn't film that, but I witnessed one of those balls that was attached to the wand, that was the metallic painted one, stayed attached to it for 3.5 hours. I saw the hollow plastic ball that's painted with a metallic paint. It stayed attached 4 inches, pulled over 4 inches from where it would hang, where the wand not there, for 1 hour. Now it was still attracted afterward, not enough to hold it 4 inches away, but so the 3.5 hour compared to an hour those are good numbers for how long this replacement lasts. It lasts for a long time. They don't just come in. Now they can dissipate very quickly sometimes, depending on the material, but in some cases they hold. And there are reasons for that. Now this is going to get, kind of complicated down the road, but we don't need to get into all that right now. We just need to understand a basic atom model that's more realistic and better than what we have now. Why we should have that, what's going on with static electricity, that negative charge is not really part of the explanation. But anyway, so these electric photons, when you put them next to that are loaded up in the PVC wand, you put it next to the bead with the aluminum foil or plastic balls or wood, or it's always attraction. But with the conductor on the surface, you get an attraction and repel. And I think what's generally happening with the attraction is that the electric photons loaded up in the wand, because you've rubbed and a lot of radio particles have been lost to the environment, and the electric photons beat them to occupy those spots. Then you're presenting a plethora or a prolificity of those as part of the environment to the bead that has a conductor on its surface. And because it has the covalent outer shell that's circulating, it's not circulating at light speed. Well, that only happens when there's an attraction involved. But a lot of those will move over into that covalent shell that's circulating in the aluminum. and that's why there's an attraction, because some of them are moving over. That's the attraction of it, and that's why they're. And when that happens, now you have a deficit in the outer shell of the wand, those atoms in the wand. You're going to have a deficit that needs to be replaced. Well, our radio particles that really are the rightful occupiers of those positions going to come in immediately and take? No, there's going to be more electric photons that beat them to restocking what was lost. And so then, as more of them build up that are transferring over into the conductor, now they're building up in the conductor, and because the electric photons have more repel, the ones that takes to supplant a radio particle, because the radio particle is also neutralizing an uncharged, generally a lower charge, not so much uncharged in electrons, but lower charged photon. They're neutralizing it. That takes away from some of their repel, so they're less repelling. So what happens is, as they transfer in to the conductor, because some of those are carrying around a little bit, and then and that gives opportunity for this plethora of some of those to jump across and take spots. So these shells are going to become more repelling in this covalence in the aluminum is going to become more repelling than it was previously. It attracts because some are transferring over. Then it builds up with more repel because the electric photons are not neutralizing a low charged photon. They're just next to one another, repelling one another, but taking the spots, and that's why you see the repel you see first the attraction, then you see the repel. There can also be holes, however, and the holes would be a hole to the nucleus. The nucleus is always going to exert an attraction if you ever have any kind of a hole at all. It's going to exert an attraction to the environment. So that's another reason why there would still be some attraction later. But when you see the attraction at first with the conductor to the wand, and then you see the reversal to repel, I think I've described that accurately. I want to read a couple of written pages that help tidy up this explanation, or these explanations of radio shells and electric current and static electricity. When you first hear this, it looks like, or there seems to be a few problems, like, for example, the transmitting of electric photons through that covalence at light speed. Here's how you solve that, and here's how you solve the other problems of the restocking. Also, the restocking, why the more natural tenants or residents of a radio shell are basically, it returns to those proportions of those after the disturbance and perfusion of electric photons is over. The reason the more repelling electric photon individuals can circulate through the material while being held in by attraction, or they couldn't attain that speed, is that even though the ones that it takes to supplant one radio unit, particle per particle, or photon digit to photon digits, that is, let's say a 5-particle radio unit with a center dark blue photon that's not uncharged but very low charge and behaves similarly with regard to charge contrast. It has these yellows, has 4 yellows on it, let's say. And to supplant that, let's say it takes 2 yellow greens and 3 yellows. And though they aren't attached, they've come in to basically supplant that R5 unit. And that's what's occupying its space electromagnetically, while that radio particle has been lost for a while. Okay. Those photon digits that are not attached exert more repel to other hovering and orbiting particles. Though they exert more repel to other hovering, orbiting particles, other radio particles in the next shell or whatever, or to one another, they are. There's another thing I have to explain when I get done finished with this. They are more attracted to the uncharged and low charged photons inside the nucleons of the nucleus of the nuclei, which makes them want to flow, so they are shared evenly over all of the nuclei of the connected atoms that are conductors. Another escalating factor for more electric photons to be added to the covalent shell is that additional repel coming in disturbs even more of the radio particles previously occupying positions in it, or still occupying. This is causing some more to be supplanted. While some initially come in, they disturb even more, which allows even more to come in and supplant even more of those. The reason the normal radio particles in that covalent shell are preferred in the long run, therefore, when the perfusion and disturbance needed to keep those supplied shuts off, that has to do with the electric photons being a bit more naturally repelled than they are to the natural or rightful radio particles to locate at that distance from a nucleus. In other words, the individual electric photons are more, repel one another more than they do were they next to a radio unit, because the radio unit has some of those same electric photons on their surfaces, but they're also neutralizing a very low charged photon, which reduces the repel. Now, okay. So without the perfusion next door, so to speak, continuing, some of those are pulled into other shells a bit when disturbances happen there, which lessen repel to those more native tenants, you might call them, of that shell distance, and some of those individuals are pulled away toward another shell as time passes. Disturbances there will let some of those want to be pulled into the next shell a little bit. This allows the more rightful resident to slowly return and take back its former proportions over the nuclei of a good conducting material. This even happens in non-conductors that likely have filled outer shells and organized their more individualized atoms, like in the PVC wand used in the static electric experiments, which would be the reason why the heightened electric loading in the outermost filled radio shells that get disturbed by rubbing with a rag or some fur or whatever revert back to former proportions of those radio particles as well, not just over covalent, in the covalent shells over nuclei, the nuclei of conductors. And then the last thing I realized I need to explain while I was reading that is that comparing radio shell particles to radio shell particles, and there are going to be at least 6 radio shells over a lot of decent sized nuclei. There might be up to 7 or 8. Depends on how you do your radio shells. I think 7 or 8 would be the max. But I've got 6 at this time. The reason, now, when you compare a complement of, let's say, electric photons it would take to do the same thing as individuals that one radio unit does in its position over a nucleus. You're comparing individuals to a unit that's connected. Okay, the radio shells, the electric photons would have more repel. Okay, not a lot, but a little, and then that unit, and they would occupy more space as well. But when you're comparing radio shell particles to radio shell particles, now all of those have a center interior low charged photon, usually not uncharged, because the uncharged are so highly attracted to the whites and the pinks, and where there's more charge contrast, that you're usually moving more into the low charge. When you're talking about radio particles, you're talking about the blue, you're talking about the dark blue being the center of those, and they're not as problematic with regard to reaction to the environment in the form of attraction. And so it doesn't take that many of these middle charged photons to cover them over and neutralize them, which is what makes a radio particle. But when you're talking about shell to shell and why the shells locate a certain distance from a nucleus, you're not comparing the small complement of whatever it takes of electric photons compared to supplant and replace a radio unit. You're not talking about that comparison. That complement of individual electric photons will always have more repel than a radio unit, because the radio unit is also neutralizing that center low charge photon. What you have with these shells of radio particles and making these spherical shells out from a nucleus is you're comparing radio particles to radio particles. They all have an interior low charged photon. And what makes those shells is the surfaces of those taking more electric type photons, say yellow and yellow green and what have you, to neutralize them. That's where there's more repel exerted away from each one of those units, which the more repel you have, the more surface repelling particles you have on those, the further out they must reside, because they have more repel. And you're not comparing those to electric photons when you're talking about the locations of these different shells. You're just talking about generally more surface repelling particles making certain class to locate at a certain distance from a nucleus. That's what you're talking about.